Welcome back to AI Podcast. Today we're digging into a fresh AAAI 2025 paper called Enhancing Decision-Making for LLM Agents via Step-Level Q-Value Models led by Yuanzhao Zhai.
I skimmed it, but say it plainly for me first. What's the one-liner?
The authors train a small, task-specific evaluator that scores each possible next action before the agent acts. The agent then picks the highest scoring move. It's like giving your LLM a quick internal coach at every step.
A coach that whispers, "Hey, that option looks better than the others." Nice. Where are these folks from?
Primarily the National University of Defense Technology, and we can shout out Zhai as lead and Tingkai as a co-author.
Great. Now, why do they need this in the first place? Aren't agents already pretty good at planning?
They're getting there, but multi-step tasks are still tricky. You click, you search, you read, you decide, and a tiny mistake early on can snowball. Most systems either rely on clever prompting or do heavy rollouts during inference, which can be slow and expensive. And fine-tuning the base model isn't always possible, especially for API models.
Right, so they're looking for something lighter than full tree search and more direct than best of n guessing.
Exactly, their idea is to learn a step-level Q-value model. Q-value just means how good is this action right now given the current state. Before deployment, they collect trajectories with Monte Carlo tree search, label which steps paid off, and turn those into preference data.
So the data is like, at this exact point, action A beat action B because it led to success down the line.
That's it. Then they train another language model with a step-level DPO objective to mimic those preferences. At runtime, the agent proposes a handful of candidate actions, the Q model scores them, and the agent executes the top pick.
I like the division of labor. One model focuses on what to do and the other acts as a critic. Does this replace prompting methods like React?
Not necessarily. Think of it as a plugin. You can still use your favorite prompting style. The Q model sits beside the agent and helps choose among the candidates those prompts produce.
What did they test this on?
Two well-known interactive settings. First, Web Shop, a simulated online shopping task where the agent searches, clicks, and buys based on constraints. Second, Hot Pot QA, a multi-hop question answering task that usually needs several retrieval and lookup steps.
And performance-wise?
On a compact base agent, scores on Web Shop roughly doubled, and Hot Pot QA saw a strong bump too, on the order of 3/4. The enhanced small agent even surpassed GPT-4 Mini in their comparisons on those tasks.
That's impressive, especially if they didn't fine-tune the base agent.
Right, the base policy can stay untouched. You train the separate evaluator offline and swap it in. That's practical for teams relying on closed models where you can't do supervised fine-tuning.
Walk me through the training loop one more time, but in everyday terms.
Sure. Imagine you're teaching a friend to navigate a new city. You run lots of practice trips with a map app that can simulate different routes. After each trip you say, "Hey, when you turned left at that intersection, it set you up for a smooth ride later. When you turned right, it led to dead ends." Those little judgments at each turn become your labeled preferences. Then you train a quick turn advisor that can glance at options and say, "Go left, not right." During a real drive, your friend proposes a few turns, the advisor scores them, and you take the best one.
Nice metaphor. What about cost and latency during inference? Sampling multiple actions sounds pricier than a single greedy decode.
It does add some overhead because you're sampling a few candidates per step, but you avoid running a whole online search tree at inference time. For many tasks, that trade-off is favorable.
Do the gains hold across different base models?
The paper reports benefits for both open source and API models, and notes the evaluator can generalize beyond the model it was trained with. The uplift varies by backbone, but the direction is consistently positive.
Were there any caveats we should keep in mind?
A few. First, results are on two benchmarks, so more domains would help stress test the idea. Second, collecting training data with tree search still costs tokens and engineering time. Third, if the environment changes a lot, like a website layout shifting, you'll want to refresh data or prompts. And finally, the evaluator itself adds compute at inference, so teams need to balance accuracy and latency.
Makes sense. Did they say anything about why web shops seem to benefit more?
My read is that tasks with richer feedback signals and more decisions per episode give the evaluator more room to help. WebShop tends to have several steps and gradations of success, so a step score can really steer you away from compounding errors.
If I'm a practitioner, how do I try this without rewriting my agent stack?
Start by logging your agent's interactions and outcomes on a target task. Use a lightweight search or curated exploration to generate alternative actions at each step. Build preference pairs from those. Train a small evaluator with a step-aware objective. Then, at runtime, have your agent sample a few action candidates and pass them through the evaluator before executing one. It's modular, so you can add it next to your existing prompting scheme.
And if I'm stuck on using an API model that I can't fine-tune, this gives me a path to task-specific guidance anyway.
Exactly. You're improving the decision policy via an external critic rather than altering the base model's weights.
What about reliability and reproducibility? Anything I should document carefully?
Prompts, environment versions, and candidate sampling settings. Those influence results a lot. Also keep the evaluator's training data and hyperparameters versioned, so you can trace which Q model was active when.
All right, give me the elevator takeaway.
Teach your agent to look before it leaps. A small step-level Q-value model, trained offline from preference data, can act as a fast critic at each decision point. It's plug-in, it works with both open and closed models, and on standard interactive benchmarks, it delivers meaningful gains.
Perfect. Kudos to Zhai and the team for a clean, practical idea. This feels like a tool many builders can adopt without blowing up their stack.
Agreed. That's it for today's AI podcast. If you're experimenting with step-level critics, send us your stories and we'll compare notes next time.
Thanks for listening. See you soon.